Okay, so also I have a really nice set of notes which I have from last year and previous years on the next section. Actually, I'm thinking, what I'm thinking of doing for all the notes that I'm doing, the PowerPoint slides, I think I'll actually just put them as a part of the Git repository in the master branch. So, so you don't have to get them every week, right? I think that's a good idea. Yeah, and I'll put them in the master branch rather than the branch for the lab, so you don't end up having to download like 10 gigabytes of PowerPoint slides every week, right? So I'll put them in the master branch. I guess I do occasionally, fix them and change them around a bit. Like I've changed around the Fraternian one, which is up on web courses now, and the ones about the component-based development are all up there as well. So right, we're starting into like the second phase of the course now. We can now position things, and orientate things, and move things around, but they don't really move. You can see even with this thing here, it moves at uniform velocity, and that's not how things move in the real world. So the second part of this course is all about physics programming, and there's two kind of tracks to this. Up until maybe about 3 weeks' time, we will program all the physics ourselves from scratch by using the equations of motion, Newtonian physics, and Hamiltonian mechanics, right? And then after that, we will say, okay, it gets a bit more complicated to do stuff like collisions. And apply joints or constraints on things, so we'll use the physics engine for the last part of the course, and that brings us up to the end of the course, right? So that's phase 2 of this course. So the first thing to say is we actually already what are physics used for in computer games? Why do we bother with them? Okay, so that's the number one thing, is get realism. Also, you get this idea of emergent gameplay. So, you can set up these physics scenarios and stuff, and it just behaves like the real world, so you don't necessarily have to script everything, right? The big players in physics, what's the biggest one?
Of course.
Huh? I would have thought Havoc is probably the biggest name in physics. Havoc do a whole lot of really cool things which are based around Havoc physics, which essentially they give away for free now. But they have a whole suite of things like Havoc animation, Havoc AI, Havoc behavior. So they do a whole suite of things which are kind of built off their physics engine. And in fact, physics itself has kind of become commoditized. The basic rigid body physics, there's millions of them out there. You can get loads of really good ones that are used in lots of game engines, including Bullet. There's loads of commercial games use the Bullet physics engine, even though it's open source and free. It's the kind of stuff that Havoc would have charged hundreds of thousands of euro for maybe 7 or 8 years ago, but now they're all free. And then there's another one called ODE, which is the Open Dynamics engine. It's kind of no longer being maintained. The one that we used to use on the course is called BPU. They all do exactly the same thing. They have a solver at their heart, which is a rigid body physics solver. And they allow you to specify stuff like the mass, the quaternion, position, a thing called the inertial tensor. So you can set up all the physics properties of an object, and then you can just step forward the time delta and give it your new position, depending on what forces are applied. And that's what physics engines do. What other physics engines are out there? There used to be a ton more.
Real?
Huh? Unreal has a physics engine. I don't know. It's not an engine. I mean, it's a game engine. Huh? Oh yeah, there's one other big one. PhysX. Is that still going?
Yeah.
That's the NVIDIA hardware accelerated physics on the GPU. Most of the physics engines do some stuff on the GPU as well, including Bullet. There's a build of Bullet which I saw at the GDC this year, and it has GPU rigid body physics, and it's able to simulate thousands and thousands of rigid body because so it does parallelizes it on the GPU. So there's loads of different physics implementations. Anyway, we'll just look at programming some simple 2D physics initially, which will start today, and then we'll move on to looking at 3D physics then after that, which is what's called Hamiltonian mechanics. So all of this physics stuff is a set of equations and values that you hold, and then you update the state of the object with respect to time. When you update the things with respect to time, does anybody know what that's called? That has a name. When you update things with respect to time. Anyone know what it's called? You might have done some, if you've done calculus, you might be used to this. It's called integration, when you update things with respect to time. So what we do in our game is we take the state of the object, its quaternion position, etc., and we integrate it. We step forward the time delta, and we calculate the new positions based on the set of equations, right? Now the equations that we're going to use are really simple. They have a name as well, and I can't remember what they're called. How many people did physics for the Leaving Cert? So you probably know all of these equations. No props. How many people did physics for the Junior Cert? Science. So you're probably familiar with some of these equations already. We'll look at the first one, right? The first one is based on, a car is traveling, let's say, at 70 kilometers an hour, and it's traveling for half an hour, how far does the car travel? 70 kilometers an hour for half an hour, it's going to travel 35 kilometers an hour. Equally, say the distance from Dublin to Galway is 250 kilometers. If I'm traveling at 70 kilometers, if I'm traveling at 100 kilometers an hour, how long will it take me? 2.5 hours, right? So we work all those things out intuitively, and we're used to dealing with this first equation of motion. The first equation of motion is, what do I call it? Do I call it P or do I call it X? Let's call it X, alright? X is equals to, velocity, X equals X plus velocity times delta T. Alright, so that's the first equation that you're already familiar with. If X is the old position, the new position is equal to the old position plus the velocity or the speed you're traveling at multiplied by how long you're traveling for. And you could rearrange that equation to solve all those problems that we just previously looked at. So, for example, another way to write that is delta X. You're familiar with delta? This symbol delta?
Yep.
Alright, so it's just a triangle and it means to change in. Alright, so the change in X is equals to the velocity times the change in time. So, like I say, you could rearrange those equations, Let's look at the two problems that we were looking at, right? The first problem we were looking at is how far have I traveled if I'm traveling at 70 kilometers an hour for half an hour. So, delta X is equals to my velocity, which is 70, multiplied by my delta T, which is half an hour. So 70 multiplied by 0.5 gives me 35. So you can see you can substitute those numbers in and it gives you the new position. The other equation we were looking at is how long does it take if I'm traveling at a certain velocity to get from between 2 points. So in this case I know delta X is equals to 250 is equals to, and I want to know how long is it going to take me. So my velocity we said was equals to 100, and that's 100 multiplied by delta T. So I now want to rearrange this in order to calculate delta T. So what do? I take 250 divided by 100 is equals to delta T. And 100 into 250 is 2.5. So there we go. I've worked out 2.5 hours by applying this equation of motion. And you can rearrange this equation of motion any way you like. So looking at delta X equals V times delta T, that can also be written as delta X over V equals delta T. And if I wanted to calculate the velocity, it's going to be delta X over delta T is equals to the velocity. So you could rearrange it in various different ways. This one is obvious, hopefully. How far you traveled, how long you take, that gives you your speed. That'll give you your speed. If I travel 100 kilometers in 1 hour, my speed is 100 kilometers an hour. If I travel 100 kilometers and it takes me 2 hours, my speed is going to be 50 kilometers an hour. Half. Everybody happy with that? That's our first equation of motion. And actually that's what we've been using to update the state of all of these things as well. The interesting and rather cool thing as well is that we can use scalars to represent some of these things, but they work better as vectors. Can you see why they work better as vectors? So X, in this example here, what should X be? It's my position, so it should be a vector. Alright? Next thing, this V is my velocity. What should that be? It should be a vector, because I want to know by how far I'm traveling, but also in what direction I'm traveling. If this was just a scalar, then I would get the distance traveled as opposed to the distance traveled in a particular direction. Does everybody follow that? So, velocity, how do we calculate velocity from speed? It's just the speed multiplied by the direction, or look vector. So you take your speed, which is a scalar, multiplied by your look vector, which is of length 1, and then it scales it. So in other words, you're traveling 5 units or 10 units in a particular direction. Do you follow? Alrighty, so that's our first equation of motion. Cool. Next equation of motion deals with the concept of acceleration. I'll write those up there and leave them up there, right? So, let's say a car is traveling at 2 meters per second, all right? And let's say after 5 seconds has elapsed, which is my delta t, is going to be equal to 5 seconds. I now discover that it's traveling at 10 meters per second. I can say that it has accelerated by 8 meters per second in 5 seconds. Isn't that fair enough? So it started at this, it ends up as this, and then this is how long it took to change its rate of acceleration. Everybody happy with that? Alright. So, what I can say is that the rate of acceleration, which is going to be acceleration is written as A, is equals to the delta V over delta S. So the change in velocity over how long it took to change the velocity gives me the rate of acceleration. And in this case, the rate of acceleration, so my delta V is going to be 10 minus 2, which is going to be 8, over 5 seconds. And that gives my rate of acceleration. Rate of acceleration is always in meters per second, or kilometers per second, or whatever. So this is going to be 5 into 8. Let me make this a slightly easier one. Let's say that's going to be 10, and then I go up as far as 20. So then I'm going to get 10 over 5. So that gives me my rate of acceleration is going to be equal to 2 meters per second per second. So this is my rate of change. My rate of change in my velocity is every second my velocity changes by 2 meters per second. So it's 2 meters per second is my velocity per second. I change my velocity. And this is called acceleration. And acceleration is given as meters per second, and that's the rate of acceleration. Does that make sense? So I'm looking at the change in velocity, right, or the delta V. Delta V over delta S. Delta V over delta T is equals to the rate of change in acceleration. And in fact, some physics books actually refer to this as the first derivative of velocity. Okay, that's just some physics book refer to it as that, first derivative. Now, there's a relationship. There's a relationship between velocity and speed and acceleration, and it's given by a really interesting little graph. Here's the graph, right? On this axis, we have time, and on this axis I have my velocity. So I've got time plotted against velocity here. When we, and this is example. Let's say at this particular time period, my velocity is 10 meters per second, and then over here, my velocity is going to be 20 meters per second. So I can see that I'm just plotting the velocity against time, and I can see that the rate of acceleration is the slope of the line here. All right, it's the rate of change in velocity per time step. The slope of the line is the acceleration. Alrighty, and remember how you calculate the slope of the line? It's y2 minus y1 over x2 minus x1. So that makes sense as well, doesn't it? Okay. An interesting thing we want to now calculate is how much is traveled if I'm accelerating at uniform acceleration. And if I'm traveling at a uniform velocity, then I just take the time multiplied by the velocity, and that gives me how far I've traveled. That makes sense? I'm traveling at 3 meters per second for 5 seconds, by one by the other. And again, you can represent that, if you like, as the area under the graph, like that. So it's, because that's length by breadth, that's the area, isn't it? Happy? So, if I'm traveling at uniform, if I am accelerating, then it's equals to this plus this bit up here. And you sum those two up together, and that will give you the distance traveled if you're accelerating or decelerating. That makes sense? So the next question is, how do we calculate, the sum of this thing here? If I'm accelerating at uniform velocity, how do I calculate, what my distance traveled is going to be? And we can work it out, right? Let's say sum of these two areas. We call that one area B, area A, and we call this one area B. And area A, how do we calculate that? That's delta T multiplied by V, isn't it? In fact, let's put two things here. Let's say that this is my starting velocity, and I'm going to call it U, and that's my end velocity, which is V. So this area under here is going to be T multiplied by U, isn't it? Which is just, change in T multiplied by the starting velocity, and that gives me area A. Alright, area B, how do you get the area of a right angle triangle like that?
Well, the other way to just take the delta T by V minus U by 2.
Perfect. That's exactly the way you do it. It's the half of the area which would be given by this here. Okay, you divide it by 2, and that gives you the area of the top part of there. Okay. So in fact, B is going to be equal to half multiplied by. So I need to calculate this here is going to be
V minus U.
B minus U. Perfect. Multiplied by delta T. So we end up with this equation here, and this is how you calculate movement with uniform acceleration. So we want to simplify this, right? V minus U is the change in is the change in velocity, right? So we can write V minus U is the same as delta V. Okay, so it's the change in velocity, and we also know that delta V is equals to the rate of acceleration A times delta T. So it's the rate of acceleration multiplied by for how long we're accelerating for. So again, if I'm accelerating at 1 meter per second or 2 meters per second for 3 seconds, after 3 seconds I will have accelerated by 2 multiplied by 3. That gives me my new velocity, right? So that's just acceleration multiplied by the delta time. And we know that that's there. So we can actually substitute in A times delta T instead of V minus U. So we end up with this thing here. Delta T times U plus a half A times delta T. And this is another very, very important physics equation. So this is how we calculate how far you've traveled if you're traveling at uniform acceleration. If you're accelerating, this is how you calculate how far you've traveled. And in fact, this can be rewritten again as U times delta T plus a half A delta T squared. Because all these are just multiplied together. And then this is a second really important physics equation. And this one here is called movement with uniform velocity. Or movement with uniform acceleration. And if you have to take the supplemental exam, you better know that. Which nobody will have to do. Alright, it's time to do a problem. Right. Little physics problem for you guys to solve. The Empire State Building is 381 meters high. I need you guys to calculate two things. Let's imagine that there's a gentleman standing at the top here, or a lady, and that person drops a coin on the top of the Empire State Building, and it proceeds down until it hits the ground. I need you to tell me two things. Number one, how long does it take? Number two, how fast is it traveling when it reaches the ground? What are we missing? Okay, so the speed of the coin initially is going to be what? We're dropping it. What's the rate of acceleration?
9.8.
Okay, very good. It's, for those of you that never did physics, it's 9.8 meters per second. And a very interesting thing is, you know, that of course is dependent on the mass of the object, isn't it? You've all seen this one, I'm sure. Look at this, right? I have these two objects, right? Heavy object, light object. Which is going to hit the ground first? The heavy object, obviously because it's heavier, isn't it? Watch, everybody watching. This is going up onto YouTube. Oh! Actually, that's not supposed to happen. Yeah, sure. So we have some air resistance. Let me pick something different, right? Let me pick this. Light and heavy. Heavy, light. We drop them both from a height. Oh my god. They both land at the same time. So what have we learned? Huh? The rate of acceleration for everything on Earth is identical regardless of the mass of the object. Why is that? Yeah, why is gravity always the same? I mean, that's kind of counterintuitive, unless you realize what gravity is. What's gravity? Gravity is a thing that pulls things together, right? Yeah, gravity is a force, right? And the force is applied to objects based on what? Their mass. So there's more gravity working on the heavy object than the lighter object, and that's why the rate of acceleration is the same. The force is bigger on heavier objects because it requires more force to get the same amount of acceleration. So, yeah.
But also the key thing, given the gravity of the Earth, it's huge mass compared to other objects.
True. Yes, quite right. But I think the main thing is that the force of gravity is dependent on the object's mass. So more force is working on this object to move it at the same rate of acceleration. And in fact, force causes acceleration. Force doesn't directly cause the object to move, but indirectly it causes it to accelerate or decelerate. Potentially, maybe not. Okay, do that. Calculate how long it takes and calculate how fast it's traveling when it reaches the ground. The video button, it doesn't actually start video. Right, so. Okay, so what's u? Our starting velocity? 0. So immediately we write this bit out because u times delta t is nothing. So basically I get delta x is equals to a half times a delta t squared. Alrighty. So delta x we know is equals to the height of the building, which is 381. So we end up with 381 equals a half. A is the rate of acceleration, so that's 9.8. And then we get delta t squared over here. So we can go 381. So then we need to divide by, we can bring all this stuff over here. A half multiplied by 9.8, so that's equals to 4. What's 9.8 divided by 2? What's that? 4.9. And then that gives me delta t squared. So then 381 divided by 4.9. 77.7 equals delta t squared. So then we get delta t is going to be equals to the square root of 77.7. And that's going to be 8.1.
8.8.
8.8. Is it 8.8?
8.8.
Cool, 8.81 seconds, right? So that's how long it takes, and then we can calculate the final velocity by knowing our starting velocity for how long we're accelerating for, and we can pick this one here. The change in velocity is equal to the rate of acceleration multiplied by the time delta. So we take the rate of acceleration, which is 9.8, and we multiply by 8.81, and that gives us our final velocity, which is
86.33.
86.3, is it?
Yeah.
Woohoo, okay. Fantastic.
Is that meters per second?
Yeah, that's meters per second. That's meters per second, because that's your final velocity. Your rate of acceleration is 9.8 meters per second.
Oh, yeah,
That's your
yeah.
final velocity. So you're traveling at 86.3 meters per second. Quick one. Why is that actually not the case? Yeah. So there's a thing which you have to use differential equations to solve called the terminal velocity. And that's the rate of acceleration will eventually stop due to the resistance of air. So air is another force, right? There's a friction force caused by the
Resistance of concrete.
What's that? Yeah, that's definitely going to cause it to stop. But the air causes friction resistance, and at some point the resistance due to the air friction is equals to the force of gravity, and therefore your object doesn't change its rate of acceleration anymore, or it doesn't change its velocity, it just stays at the same velocity. And that in physics is called the terminal velocity. There used to be a computer game years ago called Terminal Velocity. Who played it? Okay. This is almost all we need, and in fact you don't even need to use this one most of the time. All you need to use typically is to program 2D physics. You actually only need this equation. Delta x equals v times delta t. So you have to know your rate of velocity, and that's that one. What's the other one you need? Oh yeah, you need this one first. Delta v equals a times delta t. They're the two most important of the two for programming 2D physics. So first of all, you know how much your velocity changes each time delta, because you know your rate of acceleration. And then you also need to know how much your position is going to change based on your velocity. They're the two most important ones. There's one we're missing, right? And that's we need to calculate this number here, which is the acceleration. So what's the thing that causes acceleration? Well, if you're in a car, you put your foot on the accelerator, what happens? Engine goes faster. Why? More energy. What causes, force. All right. So you might imagine a car. You apply acceleration. That causes more force in the car, which causes it to move in a particular direction. Imagine a spaceship in space, right? If the spaceship has no rate of acceleration, it will just continue to move because there's no resistance. If you want it to move in a different direction, you turn the thrusters on, and that applies force to it in a particular direction. And over a number of time steps, it will start to turn in a particular direction. You follow? So we need one more equation, and that's the equation to calculate acceleration. Now, an interesting thing, I'm sure you probably know this intuitively, but if I take this object here, and if I take this object here, and I'm going to just try applying the same force to both of them, and we'll see what happens, right? So I'm going to apply the same force to both of them. Ow. So I just apply the same force to both of them, and what has happened? One has accelerated more than the other one. So what's the rate of acceleration related to? Mass. Right? And in fact, the equation is very simply, it's this. Acceleration equals the amount of force divided by the mass. So you apply a force, and the amount of acceleration that's due from that force is dependent on what's the mass of the object. Heavy objects require a lot of force to move. Light objects only require a small amount of force. But keep in mind that the force actually doesn't directly affect the position of the object. The force causes the object to accelerate or decelerate. The rate of acceleration affects the object's velocity. I mean, in the real world, there's forces being applied to everything all the time. And for example, that object there's two forces applied to it. There's the force of gravity, which is pushing the object down. And then there's an opposing force, which is caused by the fact that the object is on the surface, and that's pushing the object up. And the object then can't penetrate, Otherwise, it would keep going forever. There's an equality of forces. When the forces are equal, the object won't move at all. And you can have, you could imagine a really heavy force pushing down, a really opposite force up this way, and the object won't move at all. So the forces can sum to make a zero thing. But anyway, these are the three equations of motion. And when you implement these in a computer game, you can implement 2D steering. So you can steer things around in 2D. So your job is three things. Number one, calculate the acceleration is equals to the force over the mass. Next of all, calculate the change in velocity being equals to the acceleration times the time delta. Finally, delta x is equals to v times delta t. And that's called, in programming, this is called, it has a special name, it's called forward Euler integration function. It's called a forward Euler integration function. Now, we'll do a more complicated one, a Hamiltonian one, which incorporates the quaternion, and we'll look and how torque affects it. You know, that's next week's job. But for the class, I'm going to get you guys to implement this. A couple of other little tricky things here. If you want to implement simple steering, we also need to keep track of our look vectors or right vectors and stuff like that. How will I calculate the look vector? For simple steering. And I'll tell you how simple steering works. Simple steering basically says that the object is always looking in the direction in which it's moving. So it's not like the real world. You can't do skids, things like this. But for simple 2D steering, you say the object is always looking in the direction in which it's moving. So how do I calculate the look vector? Say again. The distance from what to what?
When you start at 3.
Yeah, but sure you have that. That's your velocity. That's your distance traveled over the time delta. That's your velocity. So how would you calculate your look vector? You always wanted to move in the direction in which you're moving. You're moving in the direction of your velocity. How do you calculate the look vector? Come on, guys. Come on, you just normalize the velocity and that gives you your look vector. You're moving in a particular velocity, you want to know which direction you're looking, just take the look is equals to the velocity over the length of the velocity vector. So you just normalize your velocity vector. This obviously only works if you're in motion. If you're not in motion, what's going to happen here? If your velocity is 0. What happens when you divide by 0? Infinity. So you only do this if your velocity is greater than 0. If the length of your velocity vector is greater than 0, you can make the look vector equals to this. One other small thing, which maybe I'm not even going to tell you, I might just let you figure it out in the lab. There's one small thing missing from this, which is going to cause our simulations to be kind of weird. I'll let you figure it out yourself. Alrighty, I think we'll finish with that for today, right?